Hello once again. In this particular video of simple linear regression, let me take forward the same problem and we'll discuss some regression statistics regarding the same problem. So we had this problem wherein the sales was a dependent variable, whereas advertised expenditure was the independent variable. Okay, and we discussed all these things in our last video, right? So let me straight away go to explain the different regression statistics, okay, which are involved in a simple linear regression. The main important regression statistic is what we call as R-square. Now this R-square is nothing but the coefficient of determination. Okay. Now when we say coefficient of determination, what it means is it is giving you some information about the goodness of the fit of the linear model with the data. That means how good or how well the model goes along with the data which is observed here. Okay, so when we get R-square as 0.845, in this case what it means is it provides you 84.5% of explanation of the changes in the dependent variable which is being explained by changes in the independent variable. What it again means is 84.5% of the changes in the dependent variable is explained by the changes in the independent variable. Okay, that means the rest of them is unexplained. Okay, so this itself suggests that there is a high degree of explanation happening in the dependent variable when there is a change in the independent variable. Like in this case, if there is some change happening in the advertisement expenditure, which is the independent variable here, you can say that 84.58% of the changes which happen in the sales is explained by the changes in the advertising expenditure. Okay, so if R-square is quite low, naturally the explanation part will come down and then the goodness of fit may not be there and it might lead to the model being insignificant. So as I had discussed in my last video, that in an ANOVA we have two aspects, regression and residual. When we say regression, we talk about explanation. Now R-square is that particular component which captures the explanation part, and so you can get the R-square from the ANOVA table like as regression sum of squares divided by total sum of squares. So how do we get this 0.845? It's basically sum of squares regression, that is 47.36 divided by the total sum of squares, that is 56. So this particular ratio will give you the value of R-square. Okay, so naturally even when we talked about F statistic, we thought that F statistic should be very high, and that can happen only when the mean sum of squares regression overshadows the mean sum of squares residual. And how do we get mean sum of squares regression higher? That is coming from the sum of squares, which you divide by degrees of freedom to get mean sum of squares, right? So in a way, it means that R square, higher R square can lead to the null hypothesis being rejected. Okay, so it's an indicator also of the significance of the model, but mainly we talk about the goodness of fit, that how well the model fits the data. That means there is not too much deviation from the linear model. Okay, right. So this is a very important regression statistic. Okay, the next regression statistic which I would like to talk about is the standard error. Now this particular standard error is basically standard error of the estimate. Now how do we get this standard error? See, you can understand the standard error as something like standard deviation. Okay, so you know that standard deviation is nothing but the square root of the variance. Now in my earlier discussion, I've already told you that mean sum of squares is kind of a pooled variance. So when we say mean sum of squares residual, that means something which is unexplained. That is, in this case, it is 1.43. Now, if you take the square root of this, you will get the standard error, which is 1.19. So the square root of mean sum of squares residual will give you the standard error of the estimate. So naturally, for goodness of fit, you would expect the standard error to be low, which in turn means that the mean sum of squares residual is low, which in turn means that the unexplained part is low, which in turn means explanation of the model is higher, thereby giving the F statistic a higher value, making the null hypothesis getting rejected. Okay, so this is how the standard error is connected to the ANOVA table. All right. Now there is yet another regression statistic called multiple R. Now generally when we say this multiple R in the case of simple linear regression, it is just a degree of association or degree of linear association rather between the independent variable and the dependent variable. So multiple R is also called as the correlation coefficient. Okay, so naturally when we say multiple R or correlation coefficient, the ranges of values which go with correlation coefficient ranges from -1 to +1. So if it's close to -1 or +1, we can say that there is a high degree of association, and thereby there might be a possibility of a linear relationship. Okay, and when we say there is a high degree of possibility, naturally it means that most of the things get explained in a linear model, and that's why you can see that when we say -1 or +1, if you square that, it will give 1, right? So that means if it's a perfectly correlated, whether it's positive or negative, you'll always get R square equal to 1, which means there is a 100% explanation of changes in the dependent variable by the independent variable, right? So see, all these things are so much connected in this way that when there is a higher correlation, we expect R square to be higher, thereby expecting explanation to be much more compared to the residual and making the model significant. Okay. So these are some of the important variables which I wanted you to understand. Now there is another regression statistic called adjusted R square, again which is not that relevant when it comes to simple linear regression. So we are not going to discuss this because even though there is a figure mentioned here, it has no relevance when it comes to only one independent variable. It has a lot of relevance only when there is a multiple linear regression where there are multiple independent variables, where you may have to make a choice about the parsimony of your model by choosing the appropriate number of independent variables, wherein adjusted R square may help in doing so. Okay. Thank you.